Yeah.
So for the z, if it's sum over all possible y's, isn't that like L to the n?
That's right. That's right. And we will talk about how you can use the forward backward algorithm to compute that efficiently, just like in HMMs, right? So you can use the forward backward algorithm to compute this efficiently. Structurally, it's the same algorithm. There's a few things have changed, but you're basically, the structure of this is the same as with the forward backward algorithm you use for estimating HMM, training HMMs.
Do you care about the z? Because like, I mean, if you're looking just from the maximum, why do you care about
You care about the z when you do training, absolutely.
Okay.
Yeah. Remember training, you were minimizing the negative of this with respect to your training data, right? And so the z absolutely appears, and it's absolutely vital to get that computed well in order to do well-calibrated training.
Yeah, when you're scoring.
Yeah, that's right. Yeah.
One last clarification. So f of y, x, y and x are vectors, right? It's a vector.
Y is a vector, x is a vector.
Okay, so when we're summing of all possible combinations of sequences of length L, and z of x.
Yes,
Of
that's
all
right.
possible sequences.
That's right. And I'll show you at towards the end of the lecture how the forward backward algorithm can compute that efficiently. Just like in HMMs, where when you do EM, the forward backward algorithm computes the expected. We'll get to it. Yeah. I'm also releasing course notes for CRFs later this week, which will have a very detailed, so that you can just read through as much detail as you'd like. Probably more than you'd like. Okay, so an operational example. Maybe this will make things a little bit more clear. So there's an x is length 2 fish sleep, and the y that we are considering is noun verb. So this is the A matrix, this is the O matrix. So this is the score of, recall that these scores are inside the exponent. The score of transitioning from noun to noun, from noun to verb, from verb to noun, from verb to verb, so on and so forth. Okay. Sorry, that's a typo. Oops, I forgot to change the notation here from last year. I'll have to do that after lecture. Okay. So basically, the idea is you just, and I apologize, the U is supposed to be an A and the W is supposed to be an O. This is notation from last year. I guess I missed it this time. Anyways, the idea is that you basically there's four things here in this thing of length 2. A transition from start to noun, a transition from noun to verb, an emission from noun to fish, and an emission from verb to sleep. There's 4 things in the summation, and if you read off what that is in this matrix, you get the total score. The total sum of these scores is e to the 4, and then the z thing is the sum over each of these possibilities, right? Each of these possibilities is noun, noun, verb, verb, noun, verb, verb, assuming that the output token space is only noun and verb. So now L equals 2 in this simple example. So these are the 4 possibilities that z sums over, and these are their exponentiated scores. So if you sort of look at this, see noun verb is actually the single most likely output sequence, and then if you sort of divide by the sum of all of them, you get that the probability, the conditional probability of noun verb given fish sleep according to this model is 66%. Yep.
But did you get the number?
I made them up for this example. Like we'll talk about training later, but assume that this model is trained. Yeah.
Is there any similar model when the variables are continuous?
Continuous.
Yes.
Yeah. So when you're continuous, you obviously can't express this as a discrete table, right? So yes, there's a version of conditional random fields called Gaussian conditional random fields. What a Gaussian conditional random field states. So if you think about it, these are just sort of somehow conditional probabilities, right? And so if you can also express conditional probabilities of continuous variables, but you need to make some structural assumptions because you can't just like, I mean, one thing you could do, which is I would not recommend, is discretize the continuous space into small buckets and learn a parameter per bucket. I would not recommend that. The other thing you do is assume that the continuous function has some shape. For example, a Gaussian shape, right? And then a Gaussian distribution is parameterized by the mean and the variance, or if it's multivariate Gaussian, the mean vector and the covariance matrix, right? And so if you assume that this model is a Gaussian conditional random field, then then everything, each of these probability tables will instead be a Gaussian probability function.
But wouldn't that be a generative model?
No, because it's still conditioned on the x.
Oh, we can, okay.
Yeah.
Condition on X, we say that
Yeah.
Y's are.
You could also have a Gaussian hidden Markov model that's continuous, that is fully generative, and you'll run into the same trade-off of where you spend your model capacity. I should also mention that Gaussian is only one of many possible continuous distributions you can use, but it's the one that's most commonly used for a variety of reasons, including the fact that it has really compact update rules, right? Because it's closed form under many update rules. But yeah, so in general, you can think of A and O not as matrices, but as functions, right? If you think of A and O as functions, then you just take in a transition from this value to this value. And if it's a Gaussian function, then it's like, what is the distance between these two divided by the standard deviation, right? The standard Gaussian assumptions, right? Right. So the more generally, you can think of A and O's as functions and not as tables. In the case where it's discrete, it's just a lookup table. Yeah.
The theist will take all the possible y's, so that kind of complexity would be too large.
That's a great question. I'm glad everyone's asking that question. It's a very important question. And I'll show you how, at the end of class, how we can compute this efficiently using forward backward. Or I guess, if you just want to compute z, I guess it's just forward. If you want to compute the gradients, you need forward backward. Well, anyways. Okay, so this is a logistic function, like, e to the something divided by the denominator. So as the scoring of this y, as the score of this y increases, so if we change our model parameters so that the score of this y increases, then the probability of this, the conditional probability of this y goes from 0 to 1 as the score becomes very negative to very positive. This is how logistic regression works, this is how conditional random field works. Conditional random field just generalizes to sequences. Okay, so this is the basic conditional random field. It directly models the conditional probability of an output sequence given an input sequence. It's a discriminator model in that sense. Makes the log linear assumption to make so the number of parameters is tractable. In fact, it has the same number of parameters as a hidden Markov model, right? I've expressed everything here in terms of an A matrix and an O matrix, which you can do for a hidden Markov model as well. Right? The only difference here is it's just like how the difference between naive Bayes and logistic regression. In naive Bayes, they made all these distribution assumptions so you can model the joint distribution. In logistic regression, it says screw it, it's just a linear model, linear scoring function inside an exponent. Here, again, it's like I have the same number of parameters, I make the same number of structural independence assumptions, but everything is otherwise it's just a sum inside an exponent, linear sum inside an exponent. Right? So you can think of this as first order sequential logistic regression. What remains? How to make predictions, how to train, extensions. All the fun stuff. Okay, prediction. Actually, you guys already know how to make predictions. If you squint, well, okay. Don't need to squint, I'll show you. So the prediction is find the highest probability sequence given a trained model. So we're not talking about training. The model is trained. Give it an input sequence. Predict the output sequence with highest probability. I can take the log. So log is a monotonic transformation. So it's equivalent to finding the sequence with the highest log probability. Right? The denominator, the z function, does not depend on y, so it doesn't factor into the argmax. So it's basically find the y that has the highest scoring rule with my scoring function, and this is the definition of my scoring function. If I were to interpret these a's and o's as the log probabilities of an HMM, it will look exactly the same, right? And so actually, if you want to make that if you want to do the maximum probability prediction, it's exactly the same as Viterbi for HMMs. You maintain a length k prefix solution for some token of this form with this scoring rule. Recursively solve for the length k plus 1 solutions, this type of scoring rule. After you've done this, you predict the best length m prefix solution. Okay. I guess just the pictorial representations, just like in HMMs. The first one is just the first prefix solution is just degenerate. It's just the base case. It's just the token. The second solution, you consider appending v for verb. You consider appending verb to each of these. You pick the one that has the highest total score according to the scoring rule. Let's say it turns out to be noun. Do the same for determiner. You pick the you pick the score that has the highest score from appending from v, determiner noun, plus the transition and emission probabilities, and so on and so forth. You store the prefix sequences, the subsequences, the best subsequences that end in each of these tokens, plus the linear scoring rule. So you want to keep track of the linear score because it's used in the next iteration. So on and so forth. Just like in HMMs, if you just think of these Fs, this F thing, this F summation is just like the log probabilities in HMM. Any questions? Okay, so one thing that Viterbi in HMMs will give you that Viterbi in conditional fields won't give you is the actual probability of the sequence, right? In HMMs, these A's and O's directly correspond to the log probabilities of the individual components of the model, and so if you just take the exponentiation of this total sum, you get the actual probability of that sequence. In conditional fields, you don't, right? You only get the score, right? In order to compute the conditional probability, you have to divide by this guy, right? Which, as many of you have commented on, seems, at least initially, intractable. Okay, so I guess we've already talked about this ad nauseam. The naive approach is A-row over all prime, exponential time. So here's how we can do it in more efficiently. So I'm going to, a little bit of notation, let G be a matrix where the entry corresponds to this term. So this is at token J. So then I can actually write the probability of, so here I'm suppressing x for brevity, because the x is constant in this entire example, the entire sequence. So we could write this probability as this, and we can also write the partition function as this. Okay, so this formula can be exploited by a concept known as a matrix semiring. You don't need to know exactly what it is. In fact, I always forget exactly what it is. But the basic idea is as follows. Suppose I want to compute. Suppose we just have a length 1 sequence, right? Or when we want to find, so J is just 1. And we want to find all the probabilities that goes from all possible A's to all possible B's. So I guess it's a length 2 sequence. Then we would just sum over, basically, then if we compute this matrix, we would just sum over this all the entries of this matrix, and we would have the Z function. So if m equals 1, then this guy is just a single product, and you just sum over all the entries of this matrix, and you're done. It turns out that we can recursively compute this G. So for example, if we want to compute the summation of the little bit of notation from G from 1 to 2, then it's basically this matrix multiplied, which is equal to this summation. And then you could, of course, recursively define this. So G from I to J is, from the ith token to the jth token, is equal to this summation of these matrices. And recall that each matrix is this form. The only thing that depends on the location you are in the sequence is the observation. So, turns out that if you do this, this guy equals this guy. So if you can efficiently compute this guy for G of 1 to M, you just sum over all the entries of this matrix. There's a path counting interpretation of what I just showed you. And again, I'm going to have all of this in the course notes released later this week in very sort of fine detail. So there's a path counting interpretation of this G matrix, right? The interpretation of the path counting is that it's the weighted path from A to B as I transition through the first emission token in the sequence. So if A and B are output tokens, so one of the L part of speech tags, and I condition on the first word in the sequence, input sequence, then it's the weighted path from going from noun to verb, or start to noun, or start to verb, right? And that weight is exactly this. Yeah?
So the very first equation, that's still a pretty big sum, right? Just to make sure that it reduces to the second one.
I'm sorry, this one?
Yeah, this sum is still.
This sum is big.
Still big, okay.
Right,
Now
and
it
then
reduces
I'm showing that if you can compute this matrix efficiently,
okay,
then
this one is all the L
quadratic in L. Quadratic in L.
Okay.
Yeah. Actually, it'll turn out to be linear in L because the only non-zero entry of A is start. Minor technical. Quadratic in L. You can just think of it as quadratic in L. The interpretation from a path counting perspective is if as we view the first word in the token, what is the weighted? All possible sequences here include all possible ways of transitioning from noun to verb while observing this word, the first word, or verb to noun, or determinant to determinant, or start to noun, or start to verb. Right, that's what this matrix corresponds to, that weighted path, right, the weight on that path. So what does it mean to count the first two? It's the weight of all paths where we transition from part of speech tag A at the beginning of prior to the first word, and transition to part of speech tag B after the second word, or at the second word. And that is this matrix product, right? This second matrix is whatever token you start in word 1, part of speech tag. I'm going to transition from that to the current word in the current part of speech tag in the second token. And that weight is exactly this term, right? And so this basically counts all possible paths from the token before the first word to the token at the second word. It basically, because of the first order decomposition, I could write it in this way. This is exactly the forward algorithm for those, or this is exactly analogous to the forward algorithm. So, I should mention that for the special case of G equals 1, this matrix is actually a vector because most of this matrix is 0 except for A equals start. Because you can't transition from, the first thing you have to transition from is start. Yeah?
So the entries will give me the probability of transitioning.
The entries are these weights, the unnormalized weights, probabilities. Recall that Z equals this, right?
Under number, okay.
Yeah. So for length 1 sequences, it's simply this. These are all possible sequences of length 1, and this is their score. For length 2 sequences, it equals this. This is all possible. This is the score of all possible sequences of length 2. For arbitrary n, looks like this. And the running time of this, is not exponential, right? It's just a bunch of matrix multiplies plus a summation at the end. And I should emphasize this is directly analogous to the Ford algorithm that you guys implemented for the homework. There are numerical instability issues when the sequence gets very large because it's e to the something times e to the something times e to the something. And so you deal with it in the standard way with normalization. Which you'll need to do for the implementation of CRFs for homework. So it's important not to forget this.
Is there an analogous where you can like take matrix logs?
For this one, let me remember. Well, it's either the log or you normalize each step. It's one or the other. I forget off the top of my head.
What do you like normalize that as a determinant, or like what do you normalize the matrices? But you can make them all like unitary or something.
It honestly loses me off the top of my head. I have this written down in my course notes. In general, you don't compute z of x directly. You compute log of z of x. That much I do remember. Because z of x is a very large number.
Yeah.
It can be a large number, right? Or a very small number. So in general, you don't actually directly compute z of x. You compute its log. And then the log of the numerator is just the f score function. Like
Yeah. It's just confusing me because like the g's don't necessarily commute, so you don't necessarily know if you can like break apart the logs in a nice way, like you can with the other stuff.
Right. Any other questions? Yeah.
Can you think that it is because we use a matrix product to reduce the complexity?
That's right. If you think about the Ford algorithm you implemented for the HMM homework, it's literally also a matrix product. Right? Because in the Ford algorithm, you have this alpha vector that you maintain at each iteration. And the alpha vector has the number of entries in the alpha vector is L, the number of tokens, right? And for each token, you compute the transition from all L other tokens from the previous time. Right? If you think of this L as a vector, it's multiplied by this matrix. This alpha as a vector, it's multiplied by a matrix of numbers. Because each one is multiplied by L numbers. Right? So it's actually directly analogous. Yeah. Like if I only care about the transition from start to one of these guys, so if in the end I don't care about the whole G matrix, just from start, then it's directly analogous to that alpha vector you keep track of. Okay, so training is done via gradient descent, just like in logistic regression. So in logistic regression, you minimize the negative log likelihood. Recall that this is equivalent to this is mathematical equivalent to finding the parameters to maximize the conditional probability of the training set, right? You just do a minimization instead of a maximization. You take the negative logs, it's a summation of the negative log probabilities, and this is exactly the log loss. So we're just doing sequential log loss, basically. Log loss over sequences. And this negative log of the probability decomposes into this. Right. Was that a question? Sorry. Okay, so the first term is easy, right? This is a linear term. This is a linear sum over a bunch of parameters, right? So the first term, okay, small typo here. So for the A parameters, the first term is just counting, and for the O parameters, the first term is also just counting. You count the number of transitions, you count the number of state part-of-speech tag word pairs, just like in hidden Markov models. Note that when I don't normalize here, right? So if you think about how this is different from hidden Markov models, in hidden Markov models I divide by something for each of these terms. I don't here because it's self-normalized, because I divide by the sum, by the partition function. So it's self-normalized in the definition of the conditional probability. So this is actually the hard part, right? This part's easy. This part's hard. And in fact, if you derive the gradient for logistic, for simple binary classification logistic regression, you have to do something here too. It was just much simpler because there are only two cases here, right? Y equals positive class and Y equals negative class. But it's more or less the same concept. It's just more complicated. So this is something that actually is directly analogous to logistic regression. If I just think of the F thing as a linear scoring rule, it's directly analogous to how it looks like for logistic regression. And so if I just apply a chain rule in linear algebra, it looks like this. And again, you can look at the course notes for more detail. And basically what happens is, so the gradient with respect to one of the transition entries, coefficients, is equal to the conditional probability of observing, basically equal to the conditional probability of observing this transition, summed over every entry in this, every token in this, every pair of tokens in this word sequence, input sequence. So this is also directly analogous to hidden Markov models. But now we're not doing like a one-step closed form formula update. This is not the closed form formula update, this is a gradient. So after we compute this, we don't just like set it to the divide by something and we're done. We actually compute this and then take a gradient step. And then we compute this again for every parameter in our model. And we take a gradient step according to this. So the gradient step of the transition probability parameter induced by the log partition function is equal to the marginal probability of observing this transition sequence over all the training examples. I know that was a mouthful to take in, but it's actually just the same as the gradient you derive for simple binary classification logistic regression. In simple binary classification logistic regression, the gradient in the first term is a simple scoring rule, the linear scoring rule, and then the log term and when you take the gradient of binary logistic regression is actually equal to just the probability. And computing this term right here, you do it with the forward backward algorithm. So here's the optimality condition of a conditional random field training problem. This is the full optimization problem. The gradient of the first part is just counting. The gradient with respect to the transition parameters. The gradient of the second part is equal to the sum over every pair of adjacent sequences the marginal probability of observing this transition. If you set this gradient equal to 0, then in optimality, the left-hand side here equal, so because this is negative, we move it over, so this equals this. So what is the optimality condition for a conditional random field parameter? The frequency count you observe in the training set should equal the conditional expectation of that transition over the training data. Right? The number of times you observe this transition in your training set should be equal to the sum of the marginal probabilities of observing that transition on the training set. This is the standard logistic regression optimality condition. You could get something analogous for simple binary. But because this doesn't have a closed form formula, to reach this optimality condition, you have to do gradient descent. So, sorry, yeah.
Just to keep track, P is again this exponential function of the sum of the certain A's and O's, right?
This P?
That's what, yeah, the P of,
Yeah.
so that's what it's contained in there.
Yeah, it's the e to the, you have to marginalize out over all the other tokens in the sequence. You know, this is the marginal over just the jth token and the j minus first token equal to b and a respectively. So you don't care about the first token, you don't care about the last token, you have to marginalize out over them.
Oh, so you don't have to sum.
Well, you have to sum over all possible y's, all possible possibilities of y's other than these two tokens.
But you don't have like exponent of the sum, you just have exponent of like, okay, yeah.
Well, P is defined as the standard form, e to the f.
Yeah.
Yeah, you just have to sum, you should have to additionally sum over all the y's that are not j token and the j minus first token as well. You marginalize out. This is just for backward for CRFs, just almost the same as in the Markov models. You could reuse this G matrix that I defined earlier. And then and once you compute these, so this is literally the forward algorithm from before. It's literally the same as the inner Markov model forward algorithm with G define something different. And then that's the Markov model. Yeah.
So you have to use like the forward algorithm twice, like once to compute G and then once to apply to this.
Okay, when you compute if you compute just the probability, this alpha vector is literally so this G is already defined. It's only a chain of G's that you need to compute use the forward algorithm for. The chain of G's is actually equivalent to this if you only care about the start transition from the start state. And again, we could do a path interpretation of the forward backward algorithm, right? We want to compute the sum over the forward algorithm wants to compute the sum over all possible paths that end in one of these tokens. Right? So you sum over all of these, and you just make that recursively, define that recursively. Matrix formulation, faster to compute, easy to implement. Recommend doing it this way.